Remember all that news about Elon Musk citing a massive DDoS attack during his audio interview with Donald Trump on X?
Oh, yeah, I remember that.
It led to some pretty significant technical glitches, didn't it? And honestly, it really made me wonder, like, what exactly happened there? How did these disruptive attacks actually work? And why are they so good at shutting things down?
Well, that's precisely what we're trying to do with this deep dive. We're going to unpack the whole concept of denial of service, or DOS, and its, let's say, bigger, badder cousin, distributed denial of service, DDoS.
Right.
Our goal really is to give you a shortcut, to understanding these digital floods. We'll explore the surprisingly varied ways they can incapacitate systems and stop legitimate users, like you, from accessing services you need online.
Okay.
We'll look at the symptoms, the telltale signs, the different types of attacks, and even how they've actually been tested out in the real world. And of course, the strategies used to fight back against them.
Okay, let's try and unpack this with a simple analogy first, because I think that really helps visualize the difference,
Good idea.
Imagine you're trying to get into, say, a really popular store, but there's just one person standing right in the entrance, deliberately blocking everyone. That's basically a denial of service attack, a DOS attack, right? Coming from just one place.
Yep, one source.
Now picture hundreds, maybe even thousands of people, all showing up at the exact same time, trying to storm that same store entrance.
Right. Chaos.
They completely overwhelm it, and suddenly nobody can get inside, not even the genuine shoppers.
That analogy, yeah, that paints a really vivid picture.
Yeah.
Because that is exactly the core difference. A DOS attack, it usually comes from a single system. It focuses its efforts on maybe one application or one server resource.
Okay.
But a distributed denial of service, a DDoS attack,
Right.
that's way more complex, much more insidious. It involves multiple attacks launched at the same time from multiple systems, often spread all over the place geographically.
So they're harder to pin down.
Exactly. That distributed nature is precisely what makes them so much harder to spot and to stop.
So, okay, if you're like caught in the middle of one of these, a DOS or a DDoS attack, what does it actually feel like from your end as the user trying to get online? What are the symptoms?
Oh, you definitely know something was wrong. You'd likely experience unusually slow performance, trying to open files, access websites. Everything just sort of crawls to a halt.
Frustrating.
Very.
Yeah.
You might find a particular website is just completely unavailable. Or in the really bad cases, you might not be able to access any website at all. It's really like the digital roads are just completely jammed up. You know, nothing can get through.
What's really interesting here, though, is that not all these digital floods are the same, are they? Some sound like brute force, just pure volume, but others seem more surgically precise.
That's right.
I'm curious how our sources break down these different attack strategies, because I imagine it's not always just about throwing as much data as possible at a target, is it?
You're absolutely right. Our sources, they actually outline 3 main types of these attacks, and each one is designed to hit a different part of the network infrastructure.
Okay, 3 types.
The first type is volume-based attacks. Like the name suggests, these are all about overwhelming the target with just sheer data volume.
The digital fire hose approach?
Pretty much, yeah. They aim to consume all the available bandwidth, literally flooding the network pipes. They're measured in bits per second, BPS. Common examples are things like UDP floods or DNS amplification attacks.
DNS amplification? What's that?
That's where attackers manipulate domain name system server, DNS servers, to bounce a huge amount of data back to the victim.
Yeah.
It sort of magnifies the attack volume.
Clever. Okay, so that's volume. Beyond just filling up the pipes, what's the next sort of lane of attack?
Well, then we have protocol-based attacks. Now, these don't necessarily aim to eat up all the bandwidth. Instead, they focus on exploiting weaknesses in the network protocols themselves.
Like finding a loophole in the rules.
Exactly. They consume server resources, things like firewalls or load balancers. And their size, it's measured in packets per second, or PPS. A really classic example here is the SYN flood. You might hear it called a half-open attack.
A SYN flood. Okay, what exactly is that? It sounds quite technical.
Well, think about how a normal connection starts, like with TCP. Your computer sends an SYN request to start things off.
Right.
The server responds with a SYN ACK, acknowledging it. And then your computer sends an ACK back to complete the handshake. 3 steps.
Okay, SYN, ACK, ACK.
A SYN flood attacker sends loads of those initial SYN requests, but then they crucially never send that final ACK.
So they leave the server hanging.
Precisely. The server is left waiting indefinitely for a response that never comes. And this ties up the server's connection resources with all these, well, half-open connections. It's like leaving thousands of phones off the hook waiting for someone to pick up. What's clever and kind of worrying is that even though it's an older attack method, it's still around because it targets something really fundamental about how TCP/IP works.
That makes sense. Are there other protocol attacks?
Yeah, another example in this category might be the ping of death, or just general ICMP floods using those ping packets to cause trouble.
Okay, so we've got sheer volume and then exploiting the rules of the road, the protocols.
Right.
But you said there's a third category, one that's maybe even more insidious, aiming for precision.
Exactly. The third type is application layer attacks. Now, these are measured in requests per second, RPs, and they are generally the most sophisticated.
Why is that?
Because they target specific web applications or services directly. And they often do it by mimicking legitimate user behavior, making them harder to detect.
Sneaky.
Very. Things like the HTTP flood fall into this category. And there's a specific, quite famous one called slow LoRa's. These attacks go straight for layer 7 protocols, usually HTTP or HTTPS.
Okay, slow Loris, we should definitely unpack that one. Our sources, they really dive deep into some specific examples of these attacks, right? And even how they're tested in controlled setups. What kind of tools do attackers actually use? And how do these digital assaults play out in practice?
Well, one powerful tool that gets highlighted is HPing3. It's a really versatile network tool. Think of it like the ping command you might know, which uses ICMP, but HPing3 lets you send custom ICMP, UDP, or TCP packets. It gives you much finer control.
So it's like a Swiss Army knife for network packets.
Kind of, yeah. It's used for all sorts of things, testing firewall rules, doing spoofed port scanning, auditing TCP/IP stacks. It's a tool that can be used by attackers, definitely, but also by security researchers trying to find vulnerabilities.
And using HPing3, our sources detail specific types of floods. Can you give us a taste of how those work beyond the SYN flood we already talked about?
Sure. So beyond the SYN flood, there's the random source attack. Here, the packets come from lots of different fake or spoofed source addresses.
Making it hard to trace back.
Incredibly difficult, yeah. Makes it hard to know who to block. Then there's the SMURF attack. This one's kind of interesting. It uses the victim's own address as the source address.
Wait, how does that work?
It sends out lots of ICMP ping requests to a whole network, but makes it look like they came from the victim. So when all the devices on that network reply...
They all reply back to the victim, a flood.
Exactly.
Yeah.
A massive flood of replies overwhelms the victim. And then there's the land attack. This sends a packet where the source and destination addresses are intentionally set to be the same, the victim's address.
So the machine tries to talk to itself.
Essentially, yes. It can cause the target machine to get stuck in a loop, trying to communicate with itself, which consumes resources and can crash it. These are all really designed to overwhelm a system right at the network level.
Okay, those sound like brute force network floods, but what about that application layer? That slow Loris attack you mentioned sounds particularly nasty because it seems so subtle. What's the trick behind it?
It is pretty nasty. Slow Loris specifically targets certain types of web servers, threaded web servers, like Apache is a common one. In these servers, each new incoming HTTP request starts a new process or thread, which takes up server resources.
Okay, one request, one thread.
Right. So slow Loris exploits this. It sends many, many incomplete HTTP requests. It starts the conversation, but never finishes it.
Incomplete how?
It sends the initial request headers, but then it just stops. And then periodically, our sources say about every 15 seconds or so, it sends just a tiny bit more incomplete header data, just enough to keep the connection alive.
So the server thinks the user is still there, just on a very slow connection.
Exactly. The server keeps waiting patiently for the complete request, tying up one of its valuable threads for each of these fake, slow connections. The attacker never actually closes the connection, if the server times out and closes one.
The attacker just opens a new one immediately.
You got it. They just keep opening new ones.
So what does this actually do to the server? And, for us trying to access a website hosted on it?
Well, it means the server's entire pool of available threads gets completely used up by these fake slow Loris connections. There are no threads left to handle legitimate requests from real users.
So the site just stops responding.
Completely. The testing detailed in our sources showed this really clearly. They set up an Apache server running XAMPP, hit it with slow Loris, and it became completely unreachable. Anyone trying to access it would just see those dreaded "this site can't be reached" messages in their browser.
Wow.
And the server logs themselves explicitly stated, server ran out of threads to serve requests. It directly shows that impact on service availability. It's exactly the kind of resource exhaustion, not necessarily bandwidth, that could lead to those technical glitches Elon Musk was talking about. It's like a silent paralysis.
Our sources even detail experiments they ran, right? With both desktop and server environments pushing them to their limits. What did those tests show about the sheer power of these floods?
Yeah, those tests were quite revealing. They really demonstrated how effective these flood attacks can be. They used different network setups, a standard 1 Gbps Ethernet link for a sort of desktop setup, and then a much faster 10 Gbps SFP link for a proper server environment.
Okay.
In both scenarios, they launched various flood attacks using H3 ICMP floods, TCP SYN floods, UDP floods, even raw IP floods.
And the results?
The results were pretty dramatic. They consistently saw a massive spike in network traffic hitting the target server. It reached near full capacity of the network link, like hitting the full 1.0 Gbps on the desktop server setup and pushing 3.5 Gbps or even more on the bigger server environment.
So it completely saturated the connection.
Absolutely. It clearly showed how successful these attacks are at just overwhelming the network resources. It really proved how devastatingly effective these floods can be in a, real-world type of scenario.
Okay, so given how potent these attacks are and how diverse they can be, how do organizations actually defend themselves? What are the counteroffensives against these digital floods? It sounds like a huge challenge.
It definitely is a challenge, but there are strategies. Mitigation usually involves multiple layers of defense, and they often need to be tailored to the specific type of attack you're seeing.
Right. No one-size-fits-all solution.
Exactly. So for ICMP floods, those ping-based attacks, effective strategies include things like setting up firewall rules to just block certain types of ICMP requests, like echo requests.
Just turn off ping.
Sometimes, yeah, or at least filter it. Also, rate limiting, basically, limiting the number of ICMP packets allowed from any single source in a given time period, and using intrusion detection systems, IDS, to spot unusual patterns of ICMP traffic.
Okay. And what about those SYN floods, the ones that tie up connections? They sound like a real pain to deal with.
They can be. For TCP SYN floods, one clever technique is called SYN cookies. When the server gets a SYN request, instead of immediately setting aside resources for that connection, it sends back a special cryptographic cookie in the SYN ACK response. Yeah, it contains encoded information about the connection. The server doesn't store anything yet. If the client is legitimate, it will send back the final ACK containing that cookie. Only then does the server verify the cookie and allocate resources.
Ah, so it delays using resources until it knows the connection is real.
Precisely. It effectively prevents the server from being overwhelmed by those half-open, fake connections. And again, rate-limiting SYN packets and using strong firewalls and, importantly, intrusion prevention systems, IPS, are crucial for detecting and actively blocking these attacks.
Makes sense. What about those big bandwidth-hogging UDP floods?
With UDP floods, things like ICMP rate limiting at the operating system level can actually help. It stops the system from being overwhelmed by error messages, like port unreachable messages, that might be generated in response to the flood. Firewall-level filtering is absolutely key here, trying to identify and discard malicious UDP traffic before it even reaches the actual application or service it's targeting. And sometimes you can use fingerprint filtering, identifying specific characteristics or patterns in the UDP packets that match known attacks and blocking those.
So multiple layers of defense seem critical. What's really fascinating, though, is that our sources don't just stop at individual attacks and defenses. They bring in the bigger picture, right? Like industry standards. It's not just about one company protecting itself. It's about the resilience of the whole digital infrastructure.
That's a really important point. It raises the question, what about the larger telecom infrastructure? Things like the 3GPP standards that govern mobile networks.
Yeah.
Our sources actually reference ITSAR, that's the Indian Telecommunications Security Assurance Requirements, and also 3GPP standards directly. And these standards explicitly state that core network elements, like the user plane function or UPF in 5G networks, must have protection built in against both network-level and application-level DDoS attacks.
Wow, so it's mandated. It's not just good practice, it's actually a requirement for these critical systems.
It is. It's a fundamental requirement for certification and deployment in many cases.
That's actually quite reassuring to hear. It means there's a baseline level of resilience expected.
Precisely. The standards, they dictate that these systems have to be able to deal with overload situations. They need mechanisms to actively prevent partial or complete impairment of system availability, as the phrasing often goes.
And how do they do that? What kind of measures?
Well, protective measures include things like restricting the amount of RAM and CPU resources any single application or process can consume, limiting the number of active sessions, prioritizing critical system processes over less important ones, and controlling the rate of transactions.
So managing resources very carefully under stress.
Exactly. And crucially, the standards also say that if an overload situation cannot be entirely prevented because some attacks might just be too massive, the system must act in a predictable, controlled way.
What does that mean, predictable?
It means, for example, a controlled system shutdown is always better than just crashing unpredictably. An uncontrolled failure could lead to data loss, corruption, or even leave the system in an insecure state. The priority is to maintain control and prevent a total loss of system protection, even under the most extreme digital pressure. It's about failing gracefully if you have to fail at all.
So we've really covered a lot there. You've learned about how, yeah, a single person, metaphorically, can shut down a major online service with a DOS attack, and how thousands working together in a DDoS attack can completely overwhelm it. You've seen the subtle yet pretty devastating tactics of attacks like Slaloris, targeting application resources rather than just bandwidth, and also the robust, multi-layered defenses that are needed to protect our digital world.
Yeah, we've explored that key difference between a single DOS and a distributed DDoS. We look at how specific protocols like TCP get exploited with things like SYN floods, and also the critical role that these network standards play in trying to ensure our digital infrastructure can actually withstand these, well, digital floods.
And this knowledge, it really is essential, isn't it? Whether you're just trying to understand breaking news like that Elon Musk example we started with, or maybe you're just curious about the unseen forces that are shaping our online experience every day. What really stands out to you from this deep dive? Maybe it's the, I don't know, the ingenious simplicity of something like a Slaloris attack, or perhaps the complexity of the layered defenses needed.